Schrödinger's cat. Perhaps the most popular cat that nobody really knows anything about. So, what is Schrödinger's cat? Well, it's a cat in a box with a radioactive isotope and a Geiger counter and a vial of poison. The radioactive isotope has a 50-50 chance of decaying, which will be detected by the Geiger counter, which will release the poison, which will kill the cat. Now, the radioactive isotope, according to quantum mechanics, is both decayed and not decayed. So the Geiger counter has both detected it and not detected it. And the poison has been both released and not released. So the cat is both alive and dead at the same time. That obviously makes no sense. And it cannot possibly be true. Most people don't really understand what the hell Schrödinger was talking about. And you know what? That's okay, because Schrödinger didn't understand it either. Paradoxes have a long history, going back to the Greek philosopher Zeno, no less, and probably older than that, who argued that motion is in fact impossible, because you move halfway to your target, then half again, then half of what remains, then half of what's left, then half and half and half and half, and you can never actually get there. He was making a philosophical point that time and space are an illusion, motion is impossible, and other stuff. What Schrödinger was arguing against was the Copenhagen interpretation of quantum mechanics, which was a school of thought founded in Copenhagen, the University of Copenhagen. And it was describing quantum mechanical phenomena. So let's say you have a wall with two slots cut into it, and behind it another wall. If you fire a gun randomly at that wall, then what you're going to get is bullets passing through those slots and hitting the wall behind. And you'll get a pattern that looks somewhat like this. Whereas if you were to fire a wave at the wall instead of particles, then those waves are going to strike those slots, and they're going to pass through the slots, making new patterns of waves. So, where the waves overlap with one another, they will interfere with one another. Peak overlaps with peak, you get constructive interference. If trough overlaps with trough, you get constructive interference. The troughs get deeper, the peaks get higher. But where peaks overlap with troughs, you get destructive interference. They cancel out. And on the far wall, you get a pattern that looks like this. Places where constructive interference happens all the time, very, very bright lines. Where destructive interference happens all the time, you get very, very dark lines. And so you get what's known as an interference pattern. Alternating bands of light and dark. Now, what happens if, instead of firing bullets or waves, what if you were to fire electrons at that wall? Would they behave like particles, or would they behave like waves? So, let's say you fire your electrons one at a time. Going to be like particles, going to be like waves. Well, it turns out they behave like waves. And that's where things get very strange, because if your electron is passing through one at a time, it's behaving like a wave, and yet, what is interfering? What is interfering with what? Well, the idea is that perhaps the electron is spread out. It's a wave, obviously, and maybe it's interfering with itself. It's passing through both slits at the same time, and interfering with itself to produce that interference pattern. So, what they did was they put an observer in front of the slot, something to see the electron before it passes through, to see if it's passing through both slots at once or only one. And suddenly it started behaving like a particle. Instead of producing the interference pattern, it just produced those two bars. So that's where scientists were left. They had this collection of facts. Electrons fired as a group will act as waves. Electrons fired individually will act as waves, possibly interfering with themselves, until you put an observer in front of the two slits, at which point they start acting like particles again. This is what the Copenhagen school, well, that's what everyone was trying to interpret. That's what they were trying to explain. So the Copenhagen interpretation is that any quantum mechanical particle is represented by what's known as a wave function, psi. That's the Greek letter psi. It represents everything about the particle that can be known. Now, a quantum mechanical particle can exist in multiple states simultaneously. Okay? So if there are two possible positions the particle can occupy, then it can be in both of them at the same time. When you observe a quantum mechanical particle, then it collapses the wave function to a single state. Okay? Meaning that the particle that was in two positions, you observe it, now it is only in one. And an electron is a quantum mechanical particle. It exists in multiple states, and therefore it can interfere with itself. And when you observe the electron before it passes through the slits, this collapses the wave functioning, preventing the interference. Okay. So ordinarily, it is a quantum mechanical particle. It exists as a wave, and then it passes through the slits and interferes with itself. But if you observe it before it passes through the slits, this collapses the wave function, turning it back into a classical particle. It no longer interferes with itself, behaves like a bullet instead of a wave. Now, Schrödinger's problem is that what was true still is true. So when you have many quantum mechanical particles, protons, neutrons, electrons, as atoms interacting with one another, they must sum to a classical object. It cannot be the case that a classical object made of quantum mechanical particles is suddenly going to start behaving like quantum mechanical objects. It must still be a classical object. This idea of observation isn't going to still hold for classical objects. Okay? We know that the act of observation doesn't change things fundamentally for you, me, and Molly McGee. So somewhere between the radioactive nuclide, the radioactive isotope, and the cat, classical truth must come back to the fore. Okay? Observation must no longer play that fundamental role. Okay? So it should not be the case that the cat is simultaneously both alive and dead. Okay? But that's what Schrödinger's understanding of the Copenhagen school told him. He thought the Copenhagen school said the cat should be both alive and dead at the same time. This is absurd. Okay? This is called a reductio ad absurdum, showing that somebody's position reduces to absurdity and therefore cannot be true. Okay? In other words, he was trying to prove the Copenhagen school of quantum mechanics false. So Schrödinger's mistake is that observation isn't observation in quantum mechanics. The scientist isn't what's important. Okay? When you look at something, or when you listen to something, those aren't observations. Okay? When light comes out of something, hits an object, strikes your eye is not where the act of observation takes place. Light striking the object is the act of observation. When a sound happens, the sound waves travel to your ear records it. Your ear is not where the observation takes place. That's when the sound is made. That's when the observation takes place. Of the classical five senses, touch is really the quantum mechanical observation. Okay? Observation is interaction in quantum mechanics. Your eye and your ear only record the observation that already took place. So we go back to the cat in the box. Okay? We have the radioactive nucleus with a 50% chance of decaying, the Geiger counter, the poison, the cat. The observer, in this case, is not the scientist. That's what Schrödinger was getting wrong. He thinks, or I should say he thought, that the observer was the scientist. He was wrong. It's not the scientist. It's not even the cat. It's not the poison. Ordinarily, it would be the Geiger counter. The Geiger counter is the thing detecting, observing, interacting with the radioactive nucleus. Okay? But in this case, it's not even the Geiger counter. In this case, the observer is the atom itself. For most quantum mechanical systems, the detector, the instrument you have in there that is interacting with the thing, would be the observer. In this case, the radioactive nucleus interacts with itself, or I should say the radioactive nucleus observes itself. It's a system that cannot simultaneously exist in the decayed and undecayed state. Okay? That's more the fault of his setup. Okay? So we change it to a different situation. There's some quantum mechanical system, and you have a detector. That detector is the observer. So in this case, the detector is the observer. It is interacting with the system. Okay? And that's where the thing falls apart. That's what Schrödinger wasn't really understanding. Okay? The cat cannot be both alive and dead at the same time. In between the quantum mechanical system and the cat, there is an observation taking place. No scientist ever said the cat would be both alive and dead. Schrödinger never said the cat would be both alive and dead. He was just trying to point out a flaw in the school of Copenhagen's interpretation of quantum mechanics. Okay? But his mistake was that he didn't understand the way they were using the word observation. For them, observation is synonymous with interaction. Okay? In quantum mechanics, it's only an observation if there's some form of interaction. And this is a one-way street. Okay? When you're, using regular everyday terms, just to be clear, it's only an observation if there's an interaction. That is to say, if you're interacting with a system, then you're performing a quantum mechanical observation. If you're observing the system, it's not necessarily a quantum mechanical observation. Finally, Deepak Chopra is full of shit. That guy just needs to stop. If you've found this explanation at all useful, then please like, comment, subscribe. Any other questions, feel free to throw them into the comments below. Thank you.